Hello class and welcome to our first week in general mathematics. For our first week, here are our learning objectives. At the end of the lesson, you should be able to first, describe the set of inputs, the function rule, and the set of outputs for a given function. Number 2, determine whether a given ordered pair, diagram, equation, or graph is a function or not. Number 3, identify a graph of function. D, determine the domain and range of a given function. E, evaluate a given function. F, perform operations involving functions. G, represent real-life situations using functions involving piecewise functions. And letter H, you should be able to solve problems involving functions. So, for our first session, we'll tackle objectives A, B, and C. For our second session, we'll tackle objectives D and E, even F. And then our third session, we'll focus on objectives G and H. By the way, objective H is under your performance task. So expect that in your performance task, I will ask you to solve problems involving functions. Let's start our discussion on the definition of function. We say that a function is a rule of correspondence between two non-empty sets. So, take note that a function is a rule in which we have to connect or relate two non-empty sets. And we call the first set the domain, while we call the second set the range. It's important to remember that for every element in the domain, in our first set, it should correspond to one and only one element in the second set. So we have here an illustration. It's like we have a machine, and what we do here is we input some value, and when we input a value, it will undergo a process. It's like it will follow some rule. What should happen to the input? After the input is processed, we will get or obtain an output. So every input has a corresponding output. So all the input are inside this non-empty set called domain, while the outputs, all the outputs, the set of outputs are contained in our range. So we have here y is equal to f of x. So we read it, y is a function of x. If you look at the highlighted letters, you will simply read this f of x. So y is a function of x. In shorthand, we say f of x, f of x, f of x. So we see functions in real life situations, like in areas of a circle. The area of a circle is a function, and it is a function of its radius. Meaning, for every radius, we will get or obtain a corresponding area. Say, if the radius of a circle is 1, then if we will plug in the value 1 to the formula a of r is equal to pi r squared, then we will get pi times 1 squared, which is equal to pi. Again, if we will substitute 2, we will input 2 to the formula, to the rule, a of r is equal to pi r squared, we will obtain an area of pi times 2 squared, which is equal to 4 pi, and so on. You see, when we input, we obtain an output, and our input are inside the set we call domain, while the output are inside our range. And this is our rule of correspondence. This is our function. Next, we have the amount of community tax, C, paid by a taxpayer whose gross income is I. So, it's obvious that the community tax that a contributor should pay depends on the gross income. If the person has a bigger gross income, then it is but right for him or her to pay a bigger community tax. So here we see a relation between community tax and gross income. Now, what variable depends on the other? Of course, it is the community tax. Our community tax is our dependent variable, while gross income is the independent one. And our input will be the independent, so our input here is gross income, while our output is community tax. Meaning, our domain is gross income, while our range is community tax. For example, if you want the collection to be fair, of course there should be a rule that will be followed. So, if a person is earning 200,000 pesos as gross, how much should she pay if he wants to request? How much should he pay as his community tax? So let's say this is our rule. If we are to interpret the rule, so let X be the gross income. If your gross income, so correction, this should be X. If your gross income is X, then we have to divide it by 1,000. Let's say that's the rule. So if we will divide 200,000 by 1,000, we will get 200 pesos. And then after dividing the gross income by 1,000, we will add it to 5 pesos. So you will have to pay 200 pesos plus this 5 pesos here. You'll have to pay 205 pesos. Now, what if you're earning 800,000 pesos? So we'll use the same rule. We will divide 800,000 by 1,000, and that is 800 pesos. We will add that to 5. So we'll pay 800 pesos. Here are some more examples. Let's try them. Now there are different ways to express a function. I've listed down 4. First is using a diagram. Second, by listing down the ordered pairs. Third, by graphing. And fourth is by writing the equation. Let's take a look at each way. First is diagramming. So we have here, you see here a diagram. So you see our first set and then our second set. This is our first, this is our second. So you see in the diagram, every element in the first set, the main, is connected to how many elements in our second set? You write if your answer is 1. The correspondence that's happening here is called 1-to-1. And when a correspondence between two relations is 1-to-1, we call that, or we say that, it is a function. Because if we go back to the definition of function, every element in the domain should correspond to one and only one element in the second set in our range. So here we have a 1-to-1 correspondence. Every element in the domain is connected to only one element in the range. 1-to-1 function. Now, we see here the difference between the many-to-one correspondence and the one-to-many correspondence. So, let's focus first on the many-to-one. So, if you're going to look at the elements 1, 2, and 3, all of them are connected to only one element in the range, which is 8. And because of that, we will say that many elements here are mapped or connected to only one element in the range. That makes it a many-to-one correspondence. And still, this is a function. It just, we still follow the definition that every element in the domain should be related to only one element in the range. So you might get confused here because we see here that many elements are connected to only one element in the range. But if you're going to think of it, 1 is connected to how many elements in the range? Just 1, 8. 2 is connected to how many elements in the range? Again, just 1. 3 connected to just 1. It just happened that the 3 of them are connected to the same element in the range, but they still follow the definition of a function. Therefore, a many-to-one correspondence is still considered function. But a one-to-many correspondence is no longer considered function. Why? Because every element, or one element, maybe one or two of the elements, are already connected to not only one but many. Like 1, it's connected to 2 elements in the range, which disqualifies it because it does not satisfy the definition. So many-to-one function, one-to-many not. Another way to express functions is by the use of ordered pairs. So we see here a diagram. Using the elements of the diagram, using the connections, we will be able to list down ordered pairs. So 1 and 4 is an ordered pair. 1, 4. Ordered because 1, 4 does not mean or is not necessarily the same as 4, 1. If you're going to change the order of the numbers inside the parenthesis, then we'll have another pair. So it's important to take note of order here. So 1, 4 is one of the ordered pairs. 2, 5 is another ordered pair. And 3, 6 is another. Are there any repeated values in our x's? Let's see. So our x's, 1, 2, 3. Because our domain should have the elements 1, 2, 3. So there's none. No element in x is repeated. What about in our range? In y, do we see any repeated values? 4, 5, 6. Obviously, none as well. So, this is a one-to-one correspondence function. Next, let's convert this diagram into the set that lists down or contains the ordered pairs. So we see 2, 4, -1, 1, 0, 0, 1, 4, 1, 1, and then 2, 4. Are there repeated values in our x's? Let's see. -2, -1, 0, 1, 2. None. Are there repeated values in our y? Yes. 1 appears in both ordered pairs. 4, they also appear in two different ordered pairs. So when there is a repetition in our y coordinates, can we still say that the list of ordered pairs illustrates a function? The answer? Yes, because the correspondence is still many to one, which means every element in the domain is connected to only one element in the range. It just happened that two elements have the same pair, like -2 and 2. They both pair with 4. But if you look at it, -2 is connected to how many elements in the domain? Just one, to 4 only. 2 is connected to how many elements in the domain? Just one, to 4 only, right? So the correspondence is meant to 1, therefore, this illustrates a function. Lastly, we have here the diagram, and we want to convert it into a list of ordered pairs. So we have 2, 6, 3, 7, 3, 8. Are there repeated values in x? The answer should be yes. 3. Are there repeated values in y? None. So this illustrates a one-to-many correspondence. Therefore, this is not a function. So we take note that when there are repeated values in x, then that's the time that we say this is not a function. But when there are repeated values in y, still this is a function. What we have to watch out for are the correspondences. We want to know if or determine if there is a one-to-one correspondence or many-to-one or one-to-many. This time, we will talk about graphs of functions. So here, I will just show you the graphs of some of the most frequently used functions in algebra. So you see here the red line, and this is horizontal. When you see a red line or a horizontal line, you have to remember that this is a graph of a constant function. When we say constant function, the form is f of x is any constant. So whatever you input here, your output does not change, hence constant. So here are some examples of a constant function. F of x is equal to 5 and f of x is equal to -2. Again, whatever you input here, the value of the function is the given constant. Next is the identity function. In the identity function, the graph is like this. If your identity function is f of x is equal to x, meaning your input is equal to your output. So when you have equal input and output, you will be able to form this line here. But if your identity function is f of x is equal to -x, then the graph will be like this. It will be falling to the right. So take note that constant function and identity function are under this bigger group of functions. Linear. Whenever a linear function or whenever a function has a graph that is a line, except when it is vertical, we say that that is a linear function. So it was introduced to you when you were in grade 8. So we have examples of linear function: 3x plus 2, 2x minus 5. So we have the slope-intercept form of linear functions. Y is equal to mx plus b. I hope this rings bells. Third, we have the graph of quadratic function. The U-shaped graph. This one. So this is a quadratic function. Some of the most basic quadratic equations are x squared and x minus 2 squared. So we have here the form usually ax squared plus bx plus c. While the V shape here is the graph of absolute value function. So when you see this symbol, these two lines, these two vertical lines with an expression inside, that means it is an absolute value function. So it's like you read it, f of x is equal to the absolute value of x minus 2. Next is the most basic or the simplest reciprocal function. F of x is equal to 1 over x, where x should not be equal to 0. So here's the graph of a reciprocal function. And then we have the square root function whose graph is like this. So the most or the simplest square root function is f of x is equal to square root of x, where x should be greater than or equal to 0. That means your x should be positive. Because if you will have a negative number inside this symbol, the square root symbol, then it will become imaginary, because the square root of a negative number is not a real number. Now, when you are given the graph of a function, how do you determine whether it is a function or not? You use the vertical line test, or the VLT. What is the vertical line test and how do you use it? A graph of a mathematical relation is a function if any vertical line drawn passing through the graph intersects the graph at exactly 1 point. So, as you can see here, those that I mentioned earlier, those graphs I've shown you are functions. For example, this constant function here, the black line, the black horizontal line. If I will draw a vertical line that passes through this horizontal line, they will intersect at this red point. So just 1 point. Also here, in our identity function, if I draw this vertical line, they will meet at just 1 point. 1 point, 1 point, 1 point, all at 1 point. So these were the 7 that I've shown you earlier. This is another graph. This is the graph of the sine function. So of all the graphs I've shown you, I know you're familiar with them, or you have seen them when you were in junior high school. But in grade 11 general mathematics, I will introduce to you 2 new functions: the greatest integer function and the piecewise function. So later, we will go back to them and tackle them with more emphasis. But first, let me show you some illustrations of graphs that are not function. So, like the circle here. The graph of circle. When you draw a vertical line along this part, you will see that the vertical line intersects the circle at 2 points. Therefore, it fails the vertical line test. So this is not a function. Same as the horizontal parabola. Same as the ellipse, the hyperbola, and the cardioid. So these are graphs of relations that are not function. Piecewise function. The rule of a piecewise function includes several definitions or formulas. Kaya nga, we call it piecewise. For example, the absolute value function is actually an example of a piecewise function. So we may express the absolute value function this way. The absolute value of x is equal to, or a of x is equal to the absolute value of x. This, when interpreted in another way, means your x or interval, your number line, shall be divided into 3 parts. The first part is 0. The second part is those numbers which are less than 0. And then the third part is those which are greater than 0. Because the value of your function when x is less than 0 is equal to the negative of what's inside. For example, absolute value of -7. So your x is -7. -7. And -7 is a number that is less than 0. So the value of your function, the rule is you have to get the negative of that. And the negative of -7 is 7. So the absolute value of -7 is 7. Okay? But when the number inside is greater than 0, meaning positive, you simply write the number. Like the absolute value of 10 is, of course, 10. While for x is equal to 0, of course, the answer is 0. So what do we mean by a piecewise function? It's like your graph is divided into pieces. So this is one piece, this is another piece, this is another. 3 pieces in all. For a second example, we see here that the rule or our function says you will use x plus 1 when the value of your x, your input, is between 0 and 2. Not including 0 and 2. Kasi walang guhit. But when your input is less than 0, the value of a will be automatically 1. But if your input is greater than 2, then you use this expression. So your number line is again divided into 3 parts. When x is between 0 and 2, so let's say this is 0, this is 2, so 0, 2. And then the part where x is less than or equal to 0, so from here, pababa. And then the part where x is greater than 2, here, pataas. So our number line is divided into 3 parts, 3 pieces. So it's like our graph is also a combination of 3 parts. A horizontal line, which is array. It's array. And then a segment, this part, the blue part, and the violet part, which is a curve. So this is divided into 3 pieces. The horizontal line or ray, the segment, and the curve. So that is all about, or that's all what you need to know about piecewise. That's all you need to know about piecewise functions. We'll talk about them more when we reach the 5th objective. Now, what is this greatest integer function? So let's say, so this is how we write the greatest integer function. we use this symbol and we place the input inside. So the g of x of this greatest integer function will be, it means this way, that the value of the greatest integer function is the greatest integer that is less than or equal to x. Say, when the number is between -2 and -1, it will be automatic that the value of the function is -2. Let's say -1.5. This number is inside this interval. So the greatest integer value of -1.5 is -2. Why? Because -2 is the greatest integer that is less than -1.5. What about the greatest integer value of -2? The answer is -2 because it is the greatest integer that is equal to x. Did you get it? Alright. What if the number is inside the interval 0 to 1? The value of that number will be 0. Say the number 0.5. We know that this number is inside this interval. And the greatest integer that is less than 0.5 is 0. Therefore, the value of this is 0. Do you get it? So that is all about the greatest integer value. And the graph of the GIF or GIF is like this. It's like stairs. The hollow circle means the number is not included. The number that corresponds to it, say 3, is not included here. Like here, say 2 is not included here. It's not part of this graph. 1, not also here. But the shaded circle means the number is included. So 2 is here, 1 here, 0 here. Alright? For our last part, what if the given is an equation? What if the function is expressed as an equation? How do you know whether the equation is that of a function or not? Let's study y is equal to x. If my x or my input is -2, then my output will be the same, -2. Since y is equal to x, then my input and output are equal. Are there repeated values in x? None. Are there repeated values in y? None as well. Therefore, the correspondence is 1 to 1, meaning this equation is that of a function. It is a function. Now, what if our function or relation is y is equal to x squared? So when I input -2 here, I get -2 raised to 2, that's -2 times -2, which is equal to +4. When I input -1, I get 1. When 0, 0, 1, 1, 2, 4. Are there repeated values in x? We don't see any. Are there repeated values in y? Yes. We see that 1 appears in both ordered pairs. 4 appears here and there. So we see that there are repetitions in the values of y. But still, we take note that this correspondence is many to 1. Like -2 and 2, -2 and 2 are both connected to 4. But if you are going to think of it, -2 is connected to how many elements here? Just 1. To 4 only. 1 and only 1. 2 is connected to 1 also. Just 1 element. And then that satisfies the definition of function. Therefore, this is a many-to-one correspondence and this is a function. X is raised to a power, y is not. What if y is raised to a power, x is not? We generate the following ordered pairs. When I input 0, my output will be 0. When I input 1, my output is also 1. When I input 4, my output will be 2 and -2. Why? Because either 2 or -2, if you're going to raise either of them to the power of -2, you will get +4. So you have 2 ordered pairs. You generate 2 ordered pairs. Also, if you will input 9, you will have 3 and -3. Are there repeated values in x? Yes. 4 and 9. 1 as well. I forgot to write here 1 and -1. Are there repeated values in y? None. So this shows a one-to-many correspondence, and that is not a function. Y is raised to a power because y should not have an exponent. So when you're given an equation, look for y and look if it is whether it is raised to a power or not. Do you have any questions so far? If none, let's answer this wrap-up question. How do you determine whether or not a given diagram, list of ordered pairs, graph, or equation is a function? After answering that question, you may now try the following practice exercises. So that's the end of my presentation. If you have any questions, you may message me. But if you don't have any, then I'll see you on our next lesson. Thank you.